All right, 3.2, the fundamental theorem and antidifferentiation. So in this section, we get a lot of vocabulary, and then what we'll do in 3.3 is put this into practice with a bunch of examples that are concrete. But right now, it's going to be a little bit of theory, a lot of vocab to go along with it. So as you can see on the left-hand side, we have an integral symbol. First time we've seen that. And this has a lower bound of a and an upper bound of b. And these are x values because of the dx here at the end. Now what sits on the inside is going to be the derivative of some function. That's f prime of x. Well, that's the derivative of f without the prime. So what we want to do is we want to know what f without the prime is, what we call the antiderivative of the derivative. And to evaluate this, what we'll do is plug in the upper bound into this antiderivative and subtract away when we plug the lower bound and evaluate that into the original function without the derivative. So one way to think about this is on the left-hand side, that integral can represent the amount of change. And that corresponds with wherever your final place is minus your starting place. So I like to think about this in terms of like our driving example, where a derivative, what's on the inside, could be like our velocity function. Then that would mean our position functions would be big F. All right, so it's kind of like if you're driving along, wherever you end up minus wherever you started, that's going to be the amount of change, say, on your car trip. So as we're thinking about this, let's think about the first example here. We have f of x. We're trying to find when we know f prime of x is 2x. So a pretty basic one to get going on here. So to do this example, what we want to think to ourselves is f is going to be some function that when I take its derivative is going to give us 2x. So at this point, I think we should be pretty confident that could be x to the second power, right? Using the power rule, that would, its derivative, f prime of x, would be 2x. But that's not the only one that would actually accomplish this. What if we said f of x was x squared plus 3? Now x squared's derivative would be the 2x. 3's derivative would be 0. So it'd still be just 2x for its derivative. And we could go further and further with this. We could attach any constant we wanted at the end. We could say plus 7. That derivative at the bottom function is still going to be 2x. So how do we account for this? Each one of these is an antiderivative of f prime of x. All right, because each one of their derivatives works out to be 2x. So it's an antiderivative, but it's not the antiderivative. All right, so just to be clear on this, there's a whole family of functions that all have that same exact derivative of 2x. So to account for all of those, what we're going to do is we find the antiderivative is we're going to say plus c at the end. So the antiderivative is going to be when you attach any constant to the end. So we put plus c where c is a constant. So some vocabulary, like I said, the antiderivative is also called the indefinite integral. So symbol-wise up here, the indefinite integral would not have these bounds of integration. So we don't have the a and the b bounding it. So our integral notation for the indefinite integral would be the integral symbol, some function on the inside here, and then dx on the outside. And this dx is going to correspond, the x is the variable that's being used in this function. So if our variable was t, you'd get a dt at the end. All right, so you got to be a little bit careful with that, but it shouldn't be too bad. All right, now I already mentioned this, but this elongated s, we call that the integral sign. Now, whatever's on the inside of this integral is referred to as the integrand. We won't use that as much, but we definitely need to know what an integral sign means. All right, so some verb forms. To express that we want to find the antiderivative, we can say we want to antidifferentiate or integrate. These mean the same things. Or find the indefinite integral of a function. All of this is antidifferentiation or integration. All right, so there's a lot of different vocabulary, and I know it's all brand new right now. Now to finish up this video, as you can see here, we have two different questions. We want to find an antiderivative of 2x. So that's what we did up above, where we said, well, x squared or x squared plus 3 or x squared plus 7, all of those work as the antiderivative of 2x. Any one of those would be a correct answer to this question. But what if we wanted to find the antiderivative of 2x? This is where you have to have x squared, but you add a plus c at the end. And that plus c can represent any constant. So it could be like the 0 we had in the first one, or the 3, or the 7, or a negative constant. It's just going to be any number attached to the end. All right, would represent the antiderivative. All right, one last example here. Let's think about the antiderivative of e to the x. So in this case, we want to pick out some function that when you take its derivative gives you e to the x. So this is one that's kind of special, that if you take the derivative of e to the x, you get e to the x. So the antiderivative of e to the x is also e to the x, but don't forget, we have to put a plus c at the end to get full credit on this. All right, hope this helps out as we're getting a lot of this vocabulary thrown our direction. We're going to use it throughout subsequent videos. Good luck.